Hello, welcome back to the fourth lecture of Introductory Astronomy. So thanks for sticking with this. Today we'll start off with an unusual picture. There is a picture of what appears to be a familiar planet, except this planet has this thing there. Now, is this CERN taken yesterday after a big black hole started to eat the Earth? Or is this something else? To the best of my knowledge, by the way, a big black hole in CERN has not started to eat the Earth. So don't run for cover. Not that there's any place you could have run for cover. But you can ponder that, and this will be answered during this potentially fascinating lecture. But first, the legally obligatory slides that say this is Physics 1600 Introductory Astronomy. Brought to you at Michigan Tech, but available worldwide. Today, we will be talking about moon phases and eclipses. Lots of pretty pictures, lots of explanation as to what that is. Next time, on Wednesday, we will be reviewing magnitudes and calendars. Why is it that Monday is Moon Day, for instance? And next time, we'll also be reviewing the astronomy pictures of the day for the previous week. So this lecture is originating today, September 15th, from Michigan Technological University in the Upper Peninsula of Michigan. I am Professor Robert Nemiroff. If you are taking this class for credit, then good for you. You can actually get credit by going to courses.mtu.edu. And you cannot get credit just from watching the lectures unless you get credit from your friends. They will give you a big hug and say, good job for following the lectures, but they will not give you course credit. So that won't help you graduate, no matter what you explain to your local registrar. There are people here, but they don't have to be here. You can get an A in this class just by watching the lectures online. But as I said, the lectures are online anyway, even for people who are not registered for the class. You are welcome no matter where you are in the world. So first, addressing the people in the class, what are you responsible for? You're responsible for the lecture material, things I say, things I mean, the correct version of what I say. You're responsible for Wikipedia entries because there's no textbook that's required for the course. You're responsible for the astronomy pictures of the day posted during the semester. You're responsible for completing the homework quizzes and the midterm and the final. The midterm isn't yet posted and the final is not yet posted. So I know I keep reviewing this every week, but sometimes people might pick up on this lecture and they're wondering what's going on. So you should have by now completed homework 1, homework quiz 1. If not, if you're just watching this and still expecting to get credit without doing things like homework 1, please see somebody because things aren't going as well as you think. Homework 2 is due soon. So please look into that, and the way you get to those, again, is at the famous courses.mtu.edu page. So I actually am going to read a little bit of mail I got this week. This won't be a email I got this week. This won't be a regular feature, but I got 2 interesting pieces of email this week. One is that from Umina Beach, Australia, John Moody writes in to say that there's an appreciative audience in Australia, and they're discussing and posting the lectures to iceinspace.com.au forum. So I don't know how many people we have down under, but you're welcome to look in on this class. Next, we have an email I got Friday from a librarian in Rome, Georgia, that asked something that many people are probably wondering. I have a question for you, Janet Webb writes. If you have time, I am currently finishing my master's in library science. Wikipedia is a hot topic in library science, and I ask why you have chosen to use it. Have you looked through it and know that astronomy is authoritative? I do not mean to sound confrontational. It is truly a topic of interest to me and based on several classes and some research I've done on my own. So there's a whole textbook cartel, and they haven't gotten me yet. So there's lots of textbook companies make lots of money, and a lot of the textbooks are actually very good. You can learn astronomy pretty well by going to a library, for instance, and taking out a textbook, or going to any bookstore that has a course in astronomy and buying the textbook and going through there and answering the questions, and you don't need anything more than that. But you can also now, that was the way, 20 years ago, that was probably your best bet of learning astronomy without taking a class. But now there's lots of online material, and the online material dwarfs the book material. In my opinion, Wikipedia entries on astronomy, particularly introductory astronomy, are very strong. This isn't true for many aspects of things, for other things outside of astronomy. For instance, there is a Wikibooks that has an astronomy textbook online, and it's really not very good. Parts of it are pretty strong, but it's just too spotty to use. But the individual entries on astronomy are very strong, and they've been looked over and edited and re-edited a lot. And they're not controversial. So one of the reasons I went with Wikipedia, because it's so good. Any textbook out there has been through several versions. I've had several people read it, and it's usually very good. But now the Wikipedia gives you more information. And supposing that the lecturer can pick out the information that's needed, I think Wikipedia is as strong as, if not stronger, than the textbooks. And what's better is it's free, and it's continually updated. Textbooks are frozen in time. So the textbook being used in most of the classes in astronomy throughout the United States, they don't know the latest thing from the Phoenix lander on Mars. All they might mention is that there is a Phoenix lander going on Mars, but we're going to talk about that. They don't include the latest eclipses, so I have pictures from some of the latest eclipses here. Although that's not crucially important to understanding topics in astronomy, it's cool to know what's going on, right? And the web allows you to do that. And Wikipedia is particularly strong in the background. And APOD is strong in the topical presences, topical things. So I would say that across the board, it might not be good to teach every class using Wikipedia, but I think there's an increasing bunch of classes, group of classes that can be taught with Wikipedia, and the students won't have to pay for a textbook, and they'll be getting something even more. I think it's going to be a while before this is adopted, because the textbook cartel is, a multi-million-dollar business, and they're just not going to give up. They currently package their things with CDs, and you can go to the textbook website, and they link to all kinds of things, although I don't think they'll be linking to APOD as much after this series of lectures, but that's fine. And they even link to Wikipedia to show that they're modern. But I think that they're an outdated mode of communication, and this is the way of the future. That's just what I think. Still, we have a textbook as background. If you like the textbook way of things, it's hard to lie down with your screen and read Wikipedia while trying not to fall asleep, and you can do that with a textbook. So there are advantages to textbooks. It's true. Okay, so I will now get off my soapbox and begin with the actual content portion of the lecture, phases of the moon. The moon, you might notice, is up in the sky at night, and it sometimes doesn't look the same. Sometimes there's this big disky thing there, and sometimes there's only part of the moon there. Where has the rest of the moon gone? Has it gone away? Is it going to come back? And the answer is, it hasn't gone away. It's just not lit up by the sun. So many of you know that already. But actually, I might have missed the lecture part here. No, where is that? Just 1 second. Here we go. This is what I wanted to do. This slide is actually out of order. It should have been the previous one. So here are your Wikipedia entries that you're responsible for. Lunar phase tells you what's coming up in this lecture too. Diurnal motion, which we will describe. Actually, we're going to hit that more next lecture. So that's not going to be that big this time. But look it up anyway. Celestial pole. What's that? Did people vote the celestial? Is that going to win the next election? Solar eclipse and lunar eclipses. So we're going to go into that in cool detail with cool pictures today. Okay, so this is online if you missed it, and you can come back and see them at any time. But I will now go to the previous one, which should have been the next one, and talk about phases of the moon. So you got your basic sun here, S, sometimes given, and then you get your basic moon here, and you have an Earth around somewhere. So the moon goes around the Earth, that's true. At any time, half of the moon and half of the Earth and half of anything in the solar system is lit up by the sun. So let's cut it in half here, so we can decide which half is the colored half. Let's do this color as the lit half. So sunlight streams out and will constantly light half the moon up, and it constantly lights half the Earth up. So it's very close to 50%. So if you're on the lit part of the Earth, you say it's daytime, because the sun is in your sky. You see the sun in your sky. People on the sun, were there to be people on the sun, and they would get sunburned pretty quickly, they would be able to see you if they had a powerful enough telescope. If you're on the dark side of the Earth, then it's nighttime and you don't see the sun. And you see lots of other suns, but they're very far away, so they don't light things up as much. Similarly, the moon, if you're on the dark side of the moon, you're one of the few people who's ever visited the moon. So you're really lucky. However, you don't see the sun. You may see the Earth. So we'll get into that. All right, so see, half of the moon is always illuminated. Only part of the lit up half is usually visible. So if you have your basic sun here, and you have your basic Earth here, I'll just write on top of stuff. In previous years when I did this, I was careful not to write on top of stuff. People know what's there. It's all right. People have the ability to look the difference between red and blue and see what I just wrote. And you have the moon here. So the moon is just outside where outside the Earth-Sun line. So if you look from the Earth to the moon here, you're going to be seeing the part of the moon that's almost completely lit up, and you will be seeing a full moon. And I have a slide that shows this in good detail. If, however, you look at the moon over here, so you're on Earth and you look over here, and wow, this just stopped working. Weird. Okay. So what did I do? Did I hit something wrong? Okay. Just a second. Technical difficulties. All right. So here's the pointer. So the Earth is here. You see the moon in this direction, and you don't see the moon fully illuminated. You see only you only see part of the moon illuminated, and therefore you only see a phase of it. Let's see, I use my finger. No, okay, things are getting bad then. The moon is locked to the Earth in the sense that the moon always shows the same face to the Earth. So when the moon orbits the Earth, you're always seeing the same part of it. So when you hear about the dark side of the moon, some people think that means the part of the moon that's always facing away from the Earth. But that's not true. The dark side of the moon is the part of the moon that always faces away from the sun. Because if it was on the light side of the moon, it would be lit up from the sun. So the dark side of the moon is sometimes where we can see it. And that's part of the moon. If you see a crescent moon, that's part of the moon that's, the crescent part is the part that's lit up, and the other part is the dark part of the moon, dark side of the moon, dark half of the moon. Okay, let's hope we can go to the next lecture, like next slide here. Oh, we were able to, okay. Still trying to clear this. All right. We're going to have some unusual things written on there because I don't know how to clear it. Okay, so we did this one lecture. Okay, so here's a picture again of, this is the sun is in this direction over here, and the Earth is in this direction over here. Here's the Earth. And so this is the time on the Earth. So if it's at noon time on the Earth, then the sun is directly overhead in this direction, okay? And it's daylight. At 3 p.m., you're getting closer to sunset, but the sun is still awake, still on the sky, so you have to look over here to see the sun. At 6 p.m., the sun is now setting over here, and this side is lit up. So at 9 p.m., it's nighttime. Midnight, it's certainly nighttime. 3 a.m., the sun hasn't risen. Then at 6 a.m. over here, the sun is rising. At 9 a.m., the sun has risen, and you can see it, and then you go around again. So every day, as the Earth spins, that happens. Now, the moon orbits the Earth in the same way that the Earth rotates, but it does it slower. So when the moon is not there, you're looking at the moon, so when the moon is in front of the sun, either you see a solar eclipse, or you don't see the moon lit up very well, because the moon has to be exactly aligned with the sun to make the sun go in eclipse. And if it's just mostly aligned with the sun and not directly in front of the sun, then you're not seeing almost any part of the moon illuminated. You just see a new moon, okay, this new moon. So then, as the moon moves about, orbits the Earth, so the moon orbits the Earth, and the Earth and moon both orbit the sun, you'll eventually see a crescent. So here we see a crescent moon here, so you only see a little bit. Then you see this says first quarter moon there, and I wish I could erase the text, but I can't just now. Then when you see more than half the moon, the first quarter moon actually appears to be half lit up. But if you think about it, you're only really seeing a quarter of it lit up. Over here is waxing gibbous. So gibbous is the other part. It's not a crescent. It's when you see more than half the moon lit up from what you can see. But there's still a dark part. A full moon, you see the whole moon lit up. Here it is gibbous again, quarter again. Now, waxing means it's increasing, and that every night you're seeing more and more of the moon lit up. And waning means it's decreasing, and every night you're seeing less and less of the moon lit up. So this diagram here, you could probably figure out now to write. It's not hard to do. But it's also very useful in figuring out logic puzzles, as we will see. Oh, so here's the moon. This is really cool. This is the moon over the time scale of a month. This is starts out new moon right now, full moon right now. So these are the quarters, here are the gibbuses. And you can see that you always see the same half of the moon, pretty much. This is a really cool image, as you can see this on APOD. It's been posted several times. You can just keep watching this for hours again until you become nauseous and need to visit the bathroom. But you can see the moon does something called librates. It slightly vibrates so that you can see a little different part of it each time. So it's not exactly lined up, but it's still mostly showing only one face. So the far side of the moon is we don't see at all, and we didn't see until recent history, until about 40 years ago, maybe 50 years ago, when the spacecraft finally went around to see the far side of the moon. So the dark side of the moon eventually grows to incorporate the whole moon. So one full lunar cycle is called a lunation and takes about a month. Okay, so sunrise versus moonrise. So the sun always rises in the east and always sets in the west. The moon also, that's dominated. The sun actually isn't really moving with respect to the Earth. It's just the Earth's rotation that's doing that. The moon also appears to rise in the east and sets in the west, as do all the stars. And again, the reason for that is the Earth's rapid rotation. The Earth is spinning about faster than the moon is going around. So to a first approximation, the moon is just static. It's like stapled into the sky. It's like one of the stars, and like the sun. And so the Earth's rotation keeps overriding it. So everything you know sets in the west. So the Earth rotates faster than the moon. Okay, so there are little puzzles like, so it sounds real easy now. Oh, I can understand this moon phase. That's obvious, right? All I didn't know was maybe these waning and waxing phases, although I've vaguely heard of them before. But here's a quiz that suddenly sounds impossible. So you're in Houghton, Michigan, let's say, at 3 p.m. during a full moon. So the logic question is, when and where is the nearest time you can see this full moon? So yeah, I give you the answer. But if you didn't know that, I mean, you can just repeat the answer, but it doesn't mean you understand. So if you really need to understand if you want to answer some of the quiz questions. So how do you do this? This thing that previously seemed obvious now seems impossible, which brings me back to one of the soapbox points of life that I like to point out, that typically in life and in astronomy and in this course, things are impossible until they're obvious. So this is one of those things. Many times you're given a problem, you just look at it and say, I don't know where to start. This is ridiculous. How can anyone expect us to know this stuff? How can you possibly know? What do you mean full moon? What is that again? Where is the full moon? It doesn't matter where a full moon is. Houghton, Michigan, why does it matter where Houghton, Michigan is? How can that fit? It's just impossible. Who could figure this out? This is ridiculous. And then when you see it, it's like obvious. It's like, well, yeah, everyone should know that. How can people not know that? And I don't know, in my opinion, a lot of life gets divided into those two dividers. The things in my life tend to be either impossible and no one could possibly understand them, and then they become totally obvious. And I guess in life, more things, as you go through life, more things go from the impossible column to the obvious column. So my job here is to make this go from the impossible column to the obvious column. And the way I do that is by going back a few slides and saying, okay, look at this. So 3 p.m., doesn't matter. Houghton, Michigan is what's called a red herring. It doesn't really matter, so long as it's, well, you get into strange things when you get near this spin poles of the Earth, but don't worry about it. So here we are at 3 p.m., and it's a full moon. So here's the full moon. So the sun's over here, and the full moon's over here. Here's where the moon has to be full. Here's your 3 p.m. So looking at this picture, How long do you have to wait till you can see the full moon? Well, at 3 p.m. you can't see it because you have to look through the Earth to see it. So that doesn't work. So 4 p.m. you still have to look through the Earth. The first time you can see the full moon, it turns out, is 6 p.m. at sunset. Because when the sun sets on this side, the moon is rising on this side. So here we see from this that the full moon is always opposite, 180 degrees opposite from the sun, a full moon. A new moon is right near the sun. So the full moon said it's all the way the other direction. So the answer to this, from looking at this picture, is obvious. So the way you solve these logic puzzles is first you say, oh my God, how could anyone possibly know that? And then you draw essentially this picture, and then you say, oh yeah, this is easy, and then you write down the answer. So that was one case of that. Okay, so eclipses. Two types, solar eclipses and lunar eclipses. So surprisingly, the solar eclipse is when the sun becomes dark. Now, the sun itself won't become dark for a long, long time, billions and billions of years. I don't expect to live to see it myself. So one trick question is, what is the phase of the sun? And the phase of the sun is always full phase. So the sun doesn't need anything to illuminate it. It's the brightest thing around. So you always see the full face of the sun. The only exception to that would be when something moves in front of it. And the biggest thing that can move in front of it is the moon. The biggest angular thing that can move in front of it is the moon. And the rare coincidence is that the moon and sun have almost exactly the same angular size. Now really, the sun is gigantic. It's just huge. We'll talk about how big it is later in the course. And the moon, well, it's bigger than you and me, but it's not as big as the sun. Compared to the sun, the moon's a little dinky thing. So how is it that this little moon can block out this big sun? Well, it happens to be much closer to us. So if something is closer to you, it has a larger angular size than things that are far away from you. So for instance, the person sitting next to you might appear to have a very large head. And this large head might appear to be roughly the same angular size as the sun. But this doesn't mean that their head is the size of the sun. No, their head is smaller, at least of people I know. So that's the way a solar eclipse works. The moon, which is actually smaller than the sun, is much closer than the sun and is approximately the same angular size as the sun. And so when it moves in front of it, it can block out most or all of it. If the moon was even closer to us, then it would block out the sun for longer periods of time during a solar eclipse. The other type of eclipse is here, the lunar eclipse. So the lunar eclipse is when the moon becomes dark. So why would the moon become dark? Well, the moon becomes dark once a month anyway, when it's right near the sun, because the part that the sun is illuminating isn't visible to us. So we're only seeing the unilluminated part of the moon, and it appears dark. But the moon, in very special circumstances, can appear dark when it's near full. And that is when the shadow of the Earth falls onto the moon, when you have near exact sun, Earth, moon alignment. So again, we've already reviewed angular size, and we've already reviewed strange coincidence. Okay, so let's go into total solar eclipses. These are spectacular. People take off from work. They spend sometimes a year or sometimes more planning to go attend a solar eclipse. Sometimes they're rained out, so they spent a year and lots of money going to some remote part of the world to see the moon totally eclipse the sun, and then it rains. Sometimes, though, and people post their eclipse stories on the web. Sometimes some of them are exciting. They're chasing it on a bicycle, trying to find an open spot, and they found a spot where there's a break in the clouds, and they're able to see a total eclipse of the sun. Sometimes it's a piece of cake. There's not a cloud anywhere, and then you just sort of wait. And people sit in lawn chairs, and you never look at the sun even when it's being eclipsed, because it's really, really bright. And so if you look directly at the sun, you'll have a really good view of the sun for a couple of seconds. And then you might see nothing for the rest of your life. So what you need to do is come up with some kind of contraption that has like a little hole in it, and then you look opposite the sun at an image of the sun. It's even worse to look at the sun through binoculars or a telescope, so don't even think of trying that. So what happens in a total solar eclipse is that the penumbra is part of the Earth that would see part of the sun eclipsed. The part of space that would see the moon totally eclipsing the sun, so you don't see the sun at all, is called the umbra, and it's really dark there. So in this picture, you can see the umbra where it's really dark. It turns out that the umbra actually touches the Earth and moves across the Earth during a total solar eclipse. So if you're in the path of totality, it's called, you will see the moon move right over the sun. Although it's less spectacular, it's easier to be in the penumbra and see the moon cover part of the sun. So a total solar eclipse is relatively rare, occurs every few years from some part. It occurs where you are, maybe only every decade or so. When the total eclipse occurs, you see what's called a solar corona, which is not generally visible when there's not a total solar eclipse. So later in life, or if you're in a lucky place to be able to see a total solar eclipse, I would advise trying to get the proper eye equipment, which could just be a piece of paper with a hole in it, looking at an image on another piece of paper to make a pinhole camera. You can see a total eclipse that way. It's fun to chase these. You get a good story, and you might actually see the total eclipse. Many times people plot out places where they think the weather's going to be good. And you can even change that at the last minute. So you get the weekly weather forecast, and you're watching it like a hawk around the area where there's supposed to be a total solar eclipse, and you try to find a place that is not clouded out. Here is what people are seeing. This is right here is a partial solar eclipse. So part of the sun is being blocked by the moon. And so these people are not currently seeing totality. They're in the penumbra, not the umbra. And still, though, it looks pretty cool. This was taken with a camera, so I was able to look at it directly. So here we see across the top. I again apologize for the things that won't disappear. So here is the sun before the moon. The moon is near it, but you just can't see it. So the moon is a new moon right now. It's not well illuminated by the sun. It's relatively dark, especially compared to the sun. So it's there, but you're just not seeing it. So in the next part of this time lapse of this eclipse in 2000, total solar eclipse over Turkey in 2006, you still see the sun. And then suddenly there's like a bite out of the sun as the moon starts to move in front of the sun. And there's even more, even more, even more, even more. Then there's just a sliver of the sun. And then the moon covers the total sun, and around you see the corona of the sun, which are outer, hotter layers, which we will cover in later lectures. Then the moon, that will be usually for a couple of minutes. It could be really short. It could be on the time scale of seconds that you see it. But you're only going to see it for a couple of minutes. Then the moon will start to move off, and eventually the sun will return to its previous glory. It's one of the strange coincidences that's not well known. Why is the angular size of the moon and the angular size of the sun about the same? Nobody really knows. It is just a really, really strange coincidence. Maybe it has something to do with the development of life on Earth, or the types of planets that would develop life. I don't know. It's very strange. People have speculated on that besides me. Okay, so here is the vanishing umbra. So here things are getting, over in this part, you can see where there's the sky is dark because the upper part of the Earth's atmosphere is not receiving sunlight because the moon is blocking it. Here you're seeing where the sky is brighter. You're seeing a really cool mountain in the distance. I think this eclipse is ending. The umbra is changing to the penumbra. The fully blocked sun is moving to the partially blocked sun, and then the moon will move off, and it will be, a decade before that part of the Earth sees it again. So these people have realized by now that this telescope wasn't doing them a lot of good. So they're out just looking toward the direction of the sun, hopefully not at the sun. Here's the picture that we started with. This is a very interesting picture. It was taken from the Mir space station before the International Space Station was set into orbit, or any part of it was set into orbit. And the astronauts on there looked back and had a really cool view of an eclipse. I really like this image because it really shows an eclipse from a different point of view. These people here in the middle, they are seeing right now a total eclipse of the sun, assuming these clouds don't cover them. These people out here are seeing a partial eclipse of the sun. This thing is zipping across the Earth, moving across the Earth. So these people over here are now, assuming they have clear skies, are now going to be able to see a total eclipse, assuming it moves in this direction. By the way, you can get on planes that try to fly and be in the maximum part of the shadow for as long as possible. They have joyrides now in several airplanes you can book. I don't think it's cheap, but I don't know how much it costs. So you're actually looking down on an eclipse here. So I think that's a really cool image. Here's another one. It doesn't always appear circular. Sometimes if you're near the limb of the Earth, the edge of the Earth, you can get a long oval. And so in this part here is where there's a total eclipse, and out here is where there's a partial eclipse, and out around there, there's no eclipse. The big corona. So if you're lucky enough to see an eclipse, here's what you see at totality. The moon totally blocks the sun, and this part of the sun, which normally is much dimmer than the center part of the sun, now is brighter than the rest of the sky. So the moon has been eclipsing the sun for as long as recorded history. And this is the first realization. They didn't know what it was, but even thousands of years ago when they saw this, you could see the corona of the sun. The corona of the sun is best seen with the eyes, not with photography. So over much of the past 150 years or so, there has been photography from the point of view, it's not digital photography. They just had photographic plates and photographic prints, and that would, light would strike it and you would see images. And that photography generally doesn't have the depth to show what dynamic range between the bright and the dim to show the truly how spectacular a total eclipse of the sun is. Recently with digital photography, well, digital photography actually has less of a dynamic range usually than regular photography. However, with Photoshop, you can take and make different parts of it brighter and dimmer, and digital manipulations, so you can approximate what the human eye sees. And here is an approximation to what the human eye sees. You can see the corona isn't just, it actually has a lot of detail and goes well out past the radius of the sun to several sun radii. We now know the corona is hot gas that is escaping the sun, some of which becomes the solar wind. People go to tremendous lengths to see an eclipse. This is a really cool picture taken of a 2005 eclipse where there's a bunch of things that are lined up. Far in the distance is the sun. Next in line is the moon. Next in line is this person who is seeing a total eclipse of the sun. And next in line is the photographer taking the picture. So there's four, and this is taken in Antarctica. So if you're too lazy to wake up to see a total eclipse, think what other people are willing to do. They're willing to hop planes that you can't get from major airports to get to Antarctica and then trek over the frozen tundra for long periods to get to a place where they can sit down in their lawn chair with their bag and their friend taking the picture and experience for themselves the total eclipse of the sun. And here it is with the corona. So this person then, assuming they return alive, which they did, I'm pretty sure, has a tremendous story to tell of the total solar eclipse that they saw. Just before or just after the total eclipse, there's something called the diamond ring. So you can see the corona around the sun, but then part of the sun suddenly peaks out and might have been visible just before, too. So it peaks out, and it's called a diamond ring because you see a ring of light around the moon, and you see a really bright part. And why is that? Why isn't the, I guess there has to be one place where the sun comes out first. But it is actually the non-roundness of the moon that becomes important here. There are mountains and valleys on the moon, and when the sun peeks through between mountains and valleys to a relative valley, then that's where if there is a bright diamond ring, that's when it appears. So this is the catchy title, I think, was written by Jerry, my co-author in APOD, When Diamonds Aren't Forever. So this diamond is going to be going away. This diamond ring is going to be going away. So I could break off and tell an interesting story for a minute here about, I used to be debated whether the moon was perfectly spherical or not. So this was a debate between Galileo and the then church, not the modern, more enlightened church, but the then church at the time of Galileo. They would preach that the moon was a perfect sphere. And so Galileo had a telescope. And so he was one of the first people ever to turn the telescope to the sky. So he turned the telescope to the sky, and he found out some obvious things. So it was impossible to see these things until you had a little telescope, and then it was obvious. For instance, Venus has phases. You can't tell that with a human eye. But you can tell it with a small telescope, even a very small telescope. The bright and dark spots on the moon, they're craters. You can see the circular craters with a small telescope, but you can't see it without. You can also see that there are mountains and valleys on the moon. So Galileo started telling people there are mountains and valleys on the moon and inviting people over to look through his telescope. And they thought that was really cool. But the church heard about it and they said, oh, no, that's not cool because the moon's a perfect sphere. So Galileo started inviting people from the Roman Catholic Church at that time to look through the telescope and say, well, what do you see? Yeah, just tell me what you see. And so they were seeing what they thought were mountains and valleys, and they didn't understand it. Because the moon's a perfect sphere, how can that be? So they came out with a proclamation that, yes, this moon appears, our moon appears to have mountains and valleys, but it is covered by a clear, transparent covering, which is perfectly spherical. So Galileo thought about that for a while, and he said, yeah, you know what? You're right. There is a transparent covering of the moon, but that transparent covering has even bigger mountains and valleys than the moon we can see. And with enough responses like that, they dragged Galileo in and made him appear before the Inquisition and made him recant all of that. Modern, though, the modern church of even the Roman Catholic Church will admit freely, the Pope is a big fan of cosmology and astronomy and will freely admit that there are mountains on the moon, and they see the universe as slightly different than they did 400 or 500 years ago. Okay, so here we see this is a distorted moon. There's something called Bailey's beads. So if you see one bead, it's a diamond ring. So this is sort of a diamond ring here. But sometimes there are several mountains and valleys that sunlight is streaming through. And someone named Bailey was one of the first people to pick this up, although it's been seen for thousands of years. So as the sun goes into total eclipse and comes out of total eclipse, here you see a sequence of images. And again, it's been stretched this way, so it takes up the whole screen. And here you see a total eclipse, but then slowly the sun comes out, and that's how it does. And you see it's slightly different in each direction because the mountains and valleys on one limb of the moon are different from the mountains and valleys on the other limb of the moon. And this was taken with the most recent eclipse that was taken just in 2008 in early August, August 1st, apparently, according to the date on this image. Okay, partial solar eclipse I've discussed before. It's when the moon only partly blocks the sun. This can happen in two ways. When you only see, like before total eclipse, there's a partial eclipse. Not the whole sun is not covered. But there's also something called an annular eclipse, and that is when the moon happens to be far enough away from the Earth so that, I can't do it with this again. So the moon here is far enough away from the Earth so that it cannot block the entire sun. If the moon was closer, it would be angularly larger. If it's far enough away, it's angularly smaller. It does not block the entire sun. And then you get something that's become more popular recently called the ring of fire. It's when you see the sun only around the edge of the moon. This is a ring of fire. So it's photogenically placed in front. The picture was taken so that there were palm trees in front. And here you see the moon is so far away that you can see the sun all the way around. And it's not perfectly centered, because it rarely would be. This is the ring of fire all the way around. Pretty cool. So this moon will never, during this time period, during this eclipse, the moon is just too angularly small to cover the entire sun. It can't happen. So you shouldn't wait up for it. When it passes in front, this is the most of the sun that's ever going to be covered during this eclipse. By the way, when people take images of this, we like there to be, it helps, in my opinion, when people send images to APOD, if they're watching, to include some foreground thing that gives it a difference in scale. So one thing I like about this is that you're seeing familiar things. You're seeing the sun, but the sun's weird. You're seeing the moon, but you don't recognize it as the moon. You see a tree in the foreground, and it's a familiar tree, and it's a different color tree. So it's also a different texture tree. So you have the texture of the clouds, you have the texture of the sun, the texture of the clouds on the sun, and you have the strange texture of the tree, and it's all taken with a single image. It's all caught together, aligned. So I think that makes it particularly interesting. That's why I like this image a lot. And this is one of the many times when we're asked, how do you pick your images for APOD? When I see an image like this, you know right away. There's not a decision-making process at this point. It's like, wow, that is really cool. And you know that you have to write it up and put it up on as an astronomy picture of the day. The sun and the moon is not the only thing that can eclipse the sun. Mercury actually eclipses the sun more frequently, but Mercury is such a small, Mercury is just about the size of the moon, a little bigger, but it's so far away from the Earth that it doesn't take away much sunlight when it passes in front. So it's not that spectacular. It doesn't take out much sunlight. Venus, though, again, doesn't take out much sunlight. You're not going to have to, turn on your reading lamps when Venus eclipses the sun, but it is a bigger dot that goes across the sun. So in 2004, there was a rare Venetian eclipse of the sun where planet Venus moved across the sun and made this chord here in this time-lapse image. And here you can see also Venus shows phases, as you can see through a telescope. And here the phase of Venus went to a completely new phase, particularly when it was right in front. And here you see a picture of the sun with Venus in front of it. This is one of my favorite Venus transits the sun's images. Again, you see a familiar sun. You see clouds, Earth clouds, covering the sun, which is not so unusual. But there is something particularly unusual. You never see a cloud that's just like that, do you? This cloud, if it was a cloud, would have been a perfectly circular, spherical cloud, and you don't see that. So what I like about this image is you look at it, it looks like, oh, some artistic image, and then you see something really weird, and you think that can't be true, but it is. This picture was taken at just the right time to catch Venus in front of the sun. So they got the artistic merit, and they got the technical timing just down at the right time to get a really cool picture. There are many pictures of the sun with Mercury in front of it, and they're basically a big white ball with a black dot. This I thought was pretty cool because here you see the most common thing to block the sun are clouds, right? So here you see clouds blocking most of the sun, and here you see little Mercury, and I think this was in 2006, or it was a rerun from an earlier. Mercury is close enough to the sun, so it, as I said, eclipses it fairly frequently. So again, this is a pretty artistic image, and it has this unusual thing if you look at it really closely, like, wow, what's that? There's Mercury. That's weird. You don't know what it is at first. You have to read the caption. Or you have to actually read the title. It says Mercury. When there's a partial eclipse of the sun, there's a really cool thing you can do. You can make pinhole cameras, as I said. You can take a piece of paper or a piece of cardboard and put a hole in it, and then put another piece of paper there, and you can see an image of the sun. And you can even see an image of the partially eclipsed sun. You see, and part of it there. But many times, many things act like pinhole cameras. In fact, trees with leaves, if it's a very sunny day and you're seeing a partial solar eclipse, the leaves of the tree will actually create lots of images of the eclipsing sun. So here you see an image here. There's thousands of images due to this tree. And who would think to look at that? But I guess people have noticed that before. But some of the cooler images we're seeing are shown, we call them eclipse trees. Other things can cause eclipses too that have little openings in them. Okay, a total lunar eclipse has the moon becoming dark. You can see the dark part of the moon due to reflected Earthlight and refracted Earthlight. The moon enters the total of the Earth's shadow, so it's sort of like the shadow of the moon on the Earth. The Earth has a shadow that the moon can enter on the other side. The difference is with a total lunar eclipse can be seen from any place that can see the moon. So if it's nighttime and there's a total lunar eclipse, no matter where you are on the Earth, if it's nighttime for you, go look at it. Just look out, and again, you can be clouded out. Assuming there's no clouds, you can see it. So it's much more common that a person can see a total lunar eclipse than a total solar eclipse. One worry that people have is how come you don't get a total lunar eclipse every full moon? And that's because the orbit of the moon is not exactly the same as the orbit of the sun. Usually the moon will go slightly above the sun or slightly below the sun. That almost happens all the time. You have to have it just the right coincidence for the moon to come in exactly on the same line as the sun, for the plane of the orbit of the moon to be intersecting the plane of the orbit of the sun. Usually they miss. Okay, so here we see when the moon goes in this line, then there is no eclipse. That's what usually happens. The moon usually misses the sun most of the time. Over here, if the moon moves into, so if you stood on the moon at this point, the Earth will be blocking part of the sun, not the entire sun. So if you were on this line, the moon would be, you would see part of the Earth blocked. And when we look back at the moon from the Earth, the moon appears slightly dimmer. Now, since the eye is what's called logarithmic, you don't notice it that much. You really have to have a good eye to notice the moon is dimmer. As part of the moon goes to be in the total, complete umbra shadow of the Earth, where when you're on the moon here, the moon is, the Earth totally blocks the sun. So if you're on the moon here, you're seeing a total solar eclipse. To the best of my knowledge, no astronaut that's landed on the moon has ever seen a total solar eclipse of the sun from the Earth. Maybe in the future. But were you to do that, you would see that. And then looking back at the moon, we see the moon would be totally dark. It's not getting any direct sunlight. But it is getting some reflected sunlight and some refracted sunlight. This is if it could go right through the middle, which it never does, and here's the other side. Here is another moving GIF, a movie. So here is where inside the Earth's penumbra is where part of the sun is blocked. Inside the Earth's umbra is when all of the sun is blocked. So here you see the moon moving through as we would see it, getting only slightly dimmer in the Earth's penumbra, and then totally blacking out, but then being lit up, as we see by the red shades of the light being refracted by the Earth there. You can also see that this part that's closer to the penumbra is generally brighter than the far part, because it's getting more refracted sunlight. It's getting no direct sunlight. It's getting more sunlight refracted through the Earth's atmosphere. Okay, here are the different parts of a lunar eclipse. All the way back in 1996, we were sent this one. It was the best thing ever at that point, and now it's only a good picture. Here you see the different parts of the moon. This is the totally eclipsed moon, but here it's changing the brightness scale so that you can see the bottom part of it is totally brighted out. And here's what you see up until then. You see the sun, the moon, more or less disappear. And then here's the totally eclipsed moon, and then you see it reappear at the bottom. Here's another time-lapse image where you see the moon disappearing. Here you see the totally eclipsed moon. It's shown to be more red. It's now lit by just a fraction of the amount of light, refracted light, and then the moon opens up again here. So this will occur during when the moon rises or sets. The moon will not stay in one part in the sky. This again will take on the time scale of half an hour to hours. Here are a bunch of images placed together so that you can see the shadow, the umbra of the Earth's shadow, in different pictures of the moon. So the moon is just placed with many different images, so it just maps out where the Earth's shadow is. Here you see that the total lunar eclipses occur every year or so. It's hard to see the dates. This is 96, 97, 2000, 2001, 2003, 2004, again 2004, 2006, 2007, the different months and days are in there. And these are the different parts of the moon. You can see that the moon, this part of the moon was really relatively bright, even though receiving no direct sunlight. It's getting a lot of refracted light from the Earth. And you can see the different redness features. The redness of the light can be dependent on how much volcanic ash is in the Earth's atmosphere at that time. Again, partial lunar eclipses are even more common, where only part of the moon is blocked out. And these also don't occur every full moon. So that will occur every, possibly every year or more commonly. People can play visual games, and so here is the, this person found out where on the sky the Earth's umbra was. And if the moon had occurred there, it would have been totally eclipsed. And where on the sky the Earth's penumbra was at this very specific moment. He then had a friend stand somewhere, and he stood with this big disk that was calculated to be exactly the size of the Earth's umbra, where it's darkest. And here you can see the moon. It was not only planned in space, it was planned in time. So the moon would be right there, and this part of the moon would be missing because it would be inside the Earth's shadow. So a very clever photograph taken by some people who did a lot of planning. Finishing up, here are the future eclipses to look forward to. Lunar eclipses, a partial eclipse will occur actually no more this year. You have to wait until 2009 to get a partial eclipse of the moon. And to get a full total lunar eclipse, it turns out you have to wait a little bit. It's, 2010. Solar eclipses actually were a little bit more lucky. There's an annular eclipse coming in January 2009. a total eclipse July 22nd of 2009. We now know exactly when these things are going to occur. And as you can see, there's an annular and total eclipse in 2010. So they probably won't come to right where you are, wherever you're seeing this. You're going to have to go on the web and look and find where they are. So if you want to go chase them, they will tell you on the web where to go. And you can probably find other people who are going to chase them and conserve resources and have more fun by going with other people to do that. So this concludes our today's lecture on eclipses. And so next time we'll talk about how bright things are and things like that, magnitudes, stuff like that. So we'll see you next time.